Hello class, this is a video tutorial on relative frequency, areas of graphs, and probability. The main focus that I'd like to get across in this quick tutorial is that the area below the curve or line of a histogram is equal to its probability. So the main thing I want you to learn from this is that area is equal to probability. And I'll demonstrate this to you using this following scenario. Let's consider the following scenario. Let's say you have cards, there's 10 of them, numbered 1 to 4. There are 4 cards numbered 1, 1 card numbered 2, 3 cards numbered 3, and so on. What is the probability of selecting each card? Well, the probability of selecting a 1, there's 4 of them out of 10. So its probability is going to be 4 out of 10. Probability of selecting a 2 is 1 out of 10. A 3 is going to be 3 out of 10, and so on. If you were to add all these values up, you would get 10 out of 10, which is equal to a total probability of 1. Now, by graphing each as a histogram or polygon, we see the relationship between the area of graphs and probability. So take a look here. I'll erase the histogram for now. So here's the histogram of the scenario that we have. And here's the polygon of the probabilities. Notice how obviously the scaling is different, but in essence, there's a distinct relationship between the area of the histogram and its probability. It'll look more obvious now if I get the polygon back. Notice how the area from, let's say, from 0 to 2, so this area, must be equivalent to the area from 1 to 2 of its probability. If calculate the sum of each rectangle of a histogram is actually equal to the sum of its frequencies. So meaning if we add this up, this is 4 by 1, 1 by 1, 3 by 1, 1 by 2. If we were to calculate those areas, it'd be a total of 4 plus 1 plus 3 plus 2, which is a sum of 10. Same goes for this one. The area from here to there is going to be 0.4 plus 0.1 plus 0.3 plus 0.2. The total area of this is going to be a total area of 1. We can show this also by calculating and graphing the cumulative frequency of distributions. We now have a cumulative probability. So the probability of a number less than or equal to our desired target. I'll take you through what this means. I want you to take note of the relationship between the probability of x and the cumulative probability. So here we go. So the probability of getting a 1 or less is 0.4, shown here. The probability of getting 2 or a 1 is going to be 0.5, shown here. So that would be the total of this area here. This area here would be 0.5. And so on. The probability of getting 3 or less is going to be 0.8. So that's from here all the way to 0. So this area here has a total of 0.8. And obviously the probability of getting 4 or less, that's everything. That's everything here. That's a total of 1, which is matching here. Let's do another example using a dice roll. So the probability of this is like so. I want you to try and imagine, this is a bit later on, if you can imagine this being a straight line. Notice the relationship between the straight line to becoming y equals x. You'll see this a bit later, that there's a distinct relationship between calculus and probability. So in summary, the relationship we will work with more is that the area of the graph of the probability of x is equal to its probability. Okay, so let's do an example together. This is actually one of your exercises. Let's do it together here. Using the following table, let's construct a histogram and polygon of the data. Well, the total for this is going to be 2 plus 5 plus 3. It's a total of 10. For 1, there's 2 of them. For 2, there are 5. And for 3, there are 3. So this is our histogram. And let's draw the polygon. Polygon starts from the center of the next numbers. That's a 0. There's 2. 2 has 5. 3 has 3. The next number will have 0. Joining these dots. Now let's calculate the area of each rectangle and polygon. Well, what do you think the total area will be? Well, let's do it here. It's going to be, let's do this as area 1. That's 1 by 2. It's area of 2 plus 1 by 5. That's area 2. It's going to be 5 plus 1 by 3. Total area of that is going to be 10. This one's slightly harder, but I'll take you through it again. Area from here, that's just the triangle. That's 1 by 2 times half. So half base times height. So it's half times 1 times 2 is 1 plus, so we're taking it from that area to this area here. It's going to be half, so the height from here is 1, so 1 over 2 plus the first, which is 2 plus 5. So that's A and B, that's the trapezoidal rule. To this, we're going to add another trapezium. Again, the height of half. Well, actually, it's going to be h on 2. That's 1 divided by 2. So h on 2 is half. So 1 on 2. A is 5 plus B is 3. And then again, the height of this next trapezium, 1 by 3 times half. 1 by 3 times half is 3 over 2. Adding all these, we get 1 plus 7 on 2, which is 3.5. This is 8 on 2, which is 4, plus 1.5. Adding all this together, we get a total of 10. So the area of these is equivalent to the total number of numbers. Now let's calculate the relative frequency and probability of each score. Okay. So the relative frequency of each, this is going to be 2 out of 10, 5 out of 10, 3 out of 10. It's a total of 10 out of 10, which is 1. Calculating the histogram for this, 2 out of 10, 5 out of 10, 3 out of 10. There we have it. Same deal for this. 2 out of 10, 5 out of 10, 3 out of 10. You can probably guess that if we try and find the total area of this, we will get the area would be 1 by 0.2 plus 1 by 0.5 is 0.5 plus 1 by 0.3 is 0.3, total of 1. We'll get the exact same thing here. You could do it alongside. You can fast forward this part. That's going to be height of 0.2 times 1 times half. It's going to be 0.1. This height here is 0.2 plus h on 2 is half times 0.2 plus 0.5 plus half. Again, the height here is 1, so h on 2 is 1 over 2 times the first, which is 0.5, and the last, which is 0.3. And lastly, we're going to add this area of the triangle, which is going to be 1 times 0.3 times half. 0.3 on 2, which is 0.15. You can probably guess, adding all of this, we get a total of 1. Okay, so I really want to emphasize again that the main idea that we're trying to get across here is that the area under a curve is its probability. So I hope to see you in the next video where we continue to expand on this. Best of luck.